Okay, I want to figure out what the force is here that we've been putting on this ball bearing with the puller. And what I measured was with the torque wrench over here. We put in a socket on here. I measured about 15 foot-pounds, and that's before these are actually yielding the arms on the puller. So just tightening this up, what I'm doing, I'm just bending these. It's not pulling the bearing out. So I'm going to go down here and show the calculation of what's going on with the force. And we'll get some little bit better light here, like that. You've got a 3/8 inch 16 screw. It's called a screw because you're tightening it with the head. It's a bolt if you tighten it with the nut. Torque is 15 foot-pounds, and you can go through and multiply by 12 and you get 180 inch-pounds. And then you can go to Shigley in machine design. The torque is equal to 0.2 times the force of the bolt times the diameter. This is called the nut factor. It has to do with the average condition of the threads of a nut, the friction. So we know the torque. We're using this factor here, which is very common in machine design, goes back 100 years. This is the force I want to solve for. The D is the 3/8 of an inch. So I'm just going to let this all be on this one side. The force is equal to the torque divided by 0.2. Divide this times the diameter. I'll flip this around. Force is equal to the torque, which is 180 inch-pounds. I just put this over here. I'm putting this over here. We'll just leave the 0.2 on the bottom. Actually, it'll be a 5 on the top. And here's 3/8 of an inch. Put an inch there. So, get the calculator out here. 180, 0.2 divide, 3 divide, 8 times. So you get 2,400 pounds. Kind of crazy. That's literally, in short tons, it would be 1.2 tons. So over here with the puller, I'm actually pulling on here with 1.2 tons, and the bearing is still stuck on there. So it's either a very, very tight fit on there, or it's glued on. That's why I'm going to cut it off. I tried heating it earlier. But anyways, this formula here that's real common is in machine design. The torque on the bolt is 0.2 times the force, that's the preload, or the tension or compression in the bolt. This is the diameter. So 3/8 of an inch is the diameter. I measured the torque. So you know the torque, you know the diameter, and just solve for the force. So there you go, you get 2,400 pounds right there, 1.2 tons. So it's kind of crazy. There you got 1.2 tons. That's a 3/8 inch bolt, you know. And so that's actually a fairly low preload. 15 foot-pounds is actually in the range of not even a grade 1 or 2 bolt. Normally you can go up probably to, I would think, maybe 30 if it's a grade 5 or something. So this is actually a fairly low torque for a 3/8 inch bolt, but here I am yielding the arms on here. So the limit here was not on this puller, isn't the screw, it's actually the arms. So if I went through and actually ground these down so they were shorter, it's going to take a larger force before these peel over. And I'll zoom in on this right here. So these are actually little pieces here that are, because there's longer, it's easier to go ahead and bend this over. If I ground these down so they were shorter, it would take, in this thing you'd have less stress, so it would be more in tension. You've got bending through this thing through here. So I could go back to the grinder and grind this down. I'm not going to do that. So If a puller's got to where the grasp is very short in line, then you're going to get a larger force before it yields on here. So there you go, like that. There's the puller that just does not have enough force on there to pull. And there we got the machine design classical formula. Torque times the nut factor is times equal to the preload times the diameter of the bolt.